Welcome everyone for the 979th monthly meeting. Today's speaker is Sarah Millholland, and she will be talking to us about the grand diversity of extrasolar winds. Going to the agenda, we'll follow the usual agenda we have. From the President's welcome, this is it. The only comment I had to make was that I attended a dark sky 24-hour virtual meeting a week ago, and I found it quite interesting, especially the mode of communication with your local administrations using some of the templates that they have provided. So I sent an email out today in the discuss group, and if you want to take it forward, Sal expressed interest in taking it further, so I don't think at this point I'm going to elaborate on it. We can probably discuss it over the emails on each of those specifics.
Two of us are like walking.
Yeah, I know. Oh my gosh, it's the club of bad backs. Comets are like cats. They have tails and they do precisely what they want. That's a David Levy quote. And of course, I put that one in because of the comet that we were looking at last month. And we'll go to the first slide. But anyways, go ahead. This is for all you sketchers, which I happen to be one. And this is the Astro Sketchers rendering of the October 10th Northern Lights after missing the display. And there it is right there. And that was shared by George Roberts. That wasn't him, but he got that off the internet and shared it with us, so I thought I'd put that one up there as well.
How many people were able to see that display in October, right?
Yeah, some of you were right here at the parking lot taking pictures. I know I drove in, it was actually active at that time.
My phone started to blow. I was out in San Diego visiting our youngest son, and my phone started to blow up at about 5 o'clock in the afternoon about all the aurora activity that everybody here in the Northeast was enjoying. So when it got dark out in San Diego, I actually took an iPhone shot of the sky to the north, and I could see a hint of pink, even as far south as San Diego, but nothing to the naked eye, and it was over. But yeah, that's a great shot, look at that.
And I just want to say, he was in we might as well spill the beans on this. He was in San Diego, and my plan was to have him on Zoom and talk to him. And of course, you see what it's like here, and I was going to say, you're in California right now, what's it like outside? And you're going to say, it's sunny. And I'd say, there is proof that the Earth is not flat. And we figured right here in Phillips Auditorium.
You still need proof?
You know what? I had a talk with a flat earther, and haven't you seen a ship go below the horizon? He said, NASA has this conspiracy, a couple of acres or something. Have you ever gone to the top of Mount Wachusett and you look one way and you see the Himalayas, and you look the other way and you see the Alps? There's a NASA, just mental block. And I'm sure it'd be the same thing. If you're sitting and say, well, in fact, he could fly around the world and he'd still come up with some conspiracy thing. So you just can't argue that.
Well, and the pink aurora, and, just to go with the non-flat Earth theory, the pink aurora from San Diego was looking north because of the curvature of the Earth. Those auroras are probably 1,000 miles away. And with the curvature of the Earth, what I was seeing was just the very top of the aurora display where it typically runs red. That's why sometimes you see pink aurora. They're pretty far away.
Aren't they closer because it's the particles interacting with the atmosphere?
Well, but it's a height sort of thing. And so
Yeah, the bottom is green. The red interacts in the atmosphere from 180 miles up to 250.
yeah, pretty high
miles
oxygen, high.
So because of the curvature of the Earth, and in fact, on May 10th, same thing. We
Yeah.
saw a lot of red here because it was a very intense storm, but it wasn't right over us, so we would have seen more green.
Yeah, it's pretty cool actually.
By the way, we did, I wasn't able to get all the comet pictures this time around, so this is one of the first ones, very representative, and it's just a couple of things on names and stuff. I think of Chris every time he's picking the new members of the club. And you have Comet Tsuchinshan, whatever you call it, Comet A. And I don't know if Michael's online at all. How do you pronounce that?
Sheck Schneider.
Sheck Schneider?
Yeah, he was a member a long time ago. He just rejoined.
What I'm going to do, I'm going to pull a plank on Chris. I'm going to secretly reply anonymously to the club. And I'm going to give a name. It's going to be one of those Eastern European names that's 27 letters long and no vowels. And then see how he pronounces it. By the way, this is a great shot. It was one of the earliest ones. I picked that, it was one of the earliest ones. A nice view, and you can see Venus over the side there. Very nice shot. It was a pretty comet. Next slide. I think we get
I see, I didn't stash some of my slides in there too. These are taken just from the light polluted Framingham over here and Acton over there. And you probably already know this, but the reason the comet was so bright was because of forward scattering of sunlight through the dust tail. Just before October 12th, the comet passed between the Earth and the Sun. And so the angle was just perfect for that. It was a dusty comet. I looked at it on October 12th also, and it was nicely orangey and very dusty tail. But of course, as the week went on, the comet was moving further away from the Sun and from the Earth, and that angle that supported the forward scattering of sunlight became, less
Effective.
less effective. Thank you. And so the comet dimmed pretty quickly. We were looking at it at a star party last week. I don't think we showed anybody the comet because it was so faint, but it's still in the evening sky. You can see it. It's gotten pretty faint though.
I think the last I saw was around 7.5 magnitude, fading away.
The first pictures was from the 12th. This was the 14th, and that was the 15th. Grandkids were looking at the comet on that one. But nice. They're not sophisticated equipment, just a cheapy Canon camera. Don't blow them up too large. They would get pretty messy.
That's right.
And so here you can see the anti-tail.
Yeah.
That's a pretty nice shot.
What's that cluster?
Yeah, that was M5, SA5.
Oh, yeah, up in there. Yeah, that was very nice.
Good shot.
M2, what's that?
What's that?
Which?
It's M5.
We'll talk about M2 though, that's coming up. Who's doing the sliding actually anyway?
You want to control it? Yeah, I can write it.
Oh, that's okay.
That's got the button.
We'll just go next.
So then I took this shot
I love
from the
this
clubhouse. It took a while for the comet to be high enough above the tree line in the west at the clubhouse, but once it did clear, it was a pretty nice thing to look at. And of course, even your iPhones today are they're really sensitive. You can hire. I've got an iPhone 14, and the May Aurora, I was shocked that I didn't even know it had a night mode until it actually did it. And it did a 3-second exposure, and I got some great Aurora shots like that. So your cameras are getting pretty sophisticated. Your phones are getting pretty sophisticated. And I think I've mentioned it before, since we're still in Solar Max, these are very sensitive Aurora detectors. Right, just point it north and snap off a 3-second exposure and see if you can see any pinks or greens. And then you know the Aurora is active. And then there's always spaceweather.com to give you all kinds of data. This is the apparition of Venus again. You've seen this slide before. I just keep moving the arrow further in time. And so we're right about where it shows now. And if you've noticed, Venus is actually becoming quite visible in the early evening skies. Still low in the southwest, but at least it's now a bit above the horizon, and it's becoming much easier to see. As it runs along in time, it'll get better through the springtime. But it'll rapidly approach inferior conjunction in the spring. And I think this inferior conjunction will put it 8 degrees away from the sun, which is a perfect time to get out there and do daytime observing. You can see Venus any day of the week. Just go out and you gotta find it, but you can see it in your telescopes quite easily. But at inferior conjunction, it's a razor-thin crescent, big because it's close to the Earth. And 8 degrees away from the sun, there's hardly any worry that you're going to blind yourself because you're going to be too close to the sun. You'll be 16 solar diameters away from the sun. That's an easy inferior conjunction to observe. And we'll talk more about that when we get there. Anyway, next slide. So as the planets go, Mercury is going to reach a greatest elongation east this weekend, 22 degrees from the sun. However, the ecliptic is still low in the evening towards the southwest. At its greatest elongation, it'll only be 8 degrees above the horizon at sunset. Better to observe Saturn, which is now transiting about 7 o'clock, 40 degrees of altitude. The rings have tilted a little over 5 degrees. And we've been showing it off at star parties. We've done 5 star parties in the last week, and everybody got a pretty good look at Saturn. Neptune, if you can ferret it out of the faint stars of Aquarius, transits about 8 o'clock at magnitude, about 8. Triton is currently at 13.8. You do need some aperture to see that. The 13.8 is pretty faint. We see it routinely with the 25-inch of the clubhouse. That's a good one. And Uranus is about 6.5 degrees southwest. The Pleiades, a little bit bigger, a little bit easier to find. Opposition is coming up later in the month. We'll wrap it up. The last two planets we care about. Jupiter, fantastic. Jupiter's here. Currently rising during the early evening at -2.8. It's almost an arc minute across. Opposition is in a few weeks, and I sent out to everybody the Great Red Spot and Shadow Transit information, and I'll continue to do that while the planet is in the evening sky. So just as you stick it on your fridge, give you a quick reminder of when things are happening, so you can get out there and check it out. Mars coming up a little bit later. It's coming up on a relatively poor apparition. The opposition is on the 15th of January, but it'll be 60 million miles away and only a 14.6 arc-second disk. Planetary imagers will have a field day with it. Lucky imaging is I guess that's the way to go. But visually, that's a pretty small disk. I bet we'll be able to see the polar caps though, or a polar cap. So that'll be pretty fun. All right, next slide, please. So again, I want to remind you of this Spica occultation coming up at the end of the month. It's the day before Thanksgiving, pre-dawn, when the very thin waning crescent moon will cover first magnitude Spica. If you've never seen a first magnitude star occulted by the moon, you should set your clock and go out and look at this one. It's pretty impressive. And the moon will not be offensively bright, so Spica will be shining brightly up until the moment it winks out. Now, it's location dependent, so check with your planetarium app to make sure you know when to be out there. Give yourself a bit of a head start, and with fingers crossed that it'll be clear, it should be a pretty impressive little display. Speaking of occultations, I know Steve and Phil and I, at separate locations, we were trying to watch the Neptune occultation the other night. Every weather app I had said it was crystal clear out. But nope, it was pretty cloudy, so that one came and went. Astronomy waits for no one, you know. So be there for this one here. All right, next slide. So here's just a finder chart for the comet in case you still want to go out there and see it. Right now it's the constellation boundaries aren't there. I think it's still in Serpens. It could be in Aquila by
Near
now.
the border of the two constellations, near their border.
Yeah, but it's still up there. If you want to grab it, you can see it telescopically. From a dark sky, I bet you could still see it with binoculars, but I think it's beyond naked eye. So I just wanted to throw that on there just to remind you that it's still up there for observing. So next slide, please. So here's our variable star of the month, part 1, T Corona Borealis. I checked it this morning, still up at 10th magnitude. It hasn't gotten bright yet. Getting very difficult to observe, and you can tell that by if you go on the AEVSO website and ask to plot the observations over the course of several days. They were jam-packed all summer long, like hundreds of observations. Now they're getting pretty few and far between, because this guy's setting pretty early in the evening skies. But good news, it's not quite circumpolar for this latitude, but you can get out there at 4:15 in the morning, it's rising up in the northeast again. So if we don't catch it in outbursts in the evening, maybe we'll catch it in the morning skies, and maybe it'll wait. The 80-year period will be up in 2026, so we'll see how that goes. But I keep tabs on that. If the minute I see there's any indication that it has gone into outburst, I'll let everybody know. So you can go out and see it or not. You won't ever I don't think any of us in this room are going to live to see it happen again. It's an 80-year cycle. All right, next slide, please. So Glenn asked me to put this up last month because he completely messed up my slide last month.
I was discombobulated last month. First of all, there's the aurora going on, so I wanted to talk fast and we could get outside and see that. And then because we couldn't get Richmond Zoom, it ruined that whole flat Earth experiment. So I was
at a playground with an 18-month-old.
And I just happened to watch online. I watched the thing online when I got home, or when it was available. And I'm blithely talking about SS Cygni, our variable star of the month. The slide behind me is talking about Algol, so I had no clue what was going on. So I told Rich, let me take this one. Algol is an eclipsing binary star. Apparently it's been known for centuries. It's called a demon star. And just a little less than every 3 days, it's a binary system, and a fainter of the two will pass in front of the brighter one. It'll go from about 2.1 magnitude to about 3.5. So it drops about a magnitude and a half, which is a substantial amount. The whole eclipse takes around 8 hours, but the guts of it is in about a 4-hour cycle. So if you get there about 2 hours before the event, you'll see the whole thing. And I just want to say, to atone for my sin, And I'll put this out later. We did do an algal evening one time at the clubhouse a while ago. It's a naked eye object, so we don't need any special equipment. But on, I think it's November 26th, it's a Tuesday night, there will be one of the minimums. And the curve minimum will be about 8 o'clock, so we want to start at about 6 to start to catch that dimming. But I'll put something out if anybody's interested. If it's just one person, I'll show up and we'll check the star out together. If we get a group of people, I might like to bring in the results, and we'll have some type of combined light curve so you can see just how things turned out. But we'll do that the next observing committee meeting.
On the 22nd, there's another relatively convenient drop to minima. The minimum occurs around local midnight, so at about 8 o'clock in the evening, the eclipse will actually start. And just to give you some reference point, here's the part of Perseus, and Algol is the beta star right here. At minimum, it's about equal in brightness to Rho, right here. So you can always, if you just take a quick glance up at Perseus, and you can look at Algol and Rho, they're right next to each other in the sky, and you can tell in an instant if Algol is dropping towards the minimum. But that's a fun observation because you can do it quickly and you can get some great data for it.
That was the one that's the one just before the one I was talking about.
Yeah.
If anybody, if you're an all-nighter, we'll do that one instead. But
If you want to find a convenient place to find the times of these minima is in the Canadian handbook, the Royal Astronomical Society handbook. They list them all year long.
and they're in Sky and Telescope as well.
Oh, okay, great. All right, so next slide. So the double star of the month is Omicron 2 Eridani. I think it's pronounced Kid. 40 Eridani. It's probably the easiest white dwarf star in the sky for you to observe with your telescopes. This is actually a triple star system. And it's a little early in the season to put it up there, but I just wanted to make you all aware of it. So there's Orion the Hunter in this constellation chart. And so you just float along Eridanus for a little ways until you get to the pair of stars that are highlighted there. And telescopically, they're magnitude 4.4, 9.7, and 11.2. The 4.4 magnitude star is a yellow main sequence star. The white dwarf is at magnitude 9.7, and the red dwarf, which is actually kind of hard to see, is 11.2. It's a really cool triple star system.
The colors, it's beautiful.
Yeah, it's really very colorful, but the real bonus for going there is you get to observe for yourself a white dwarf star. There are only a handful that you can see in the sky. Sirius B. Has anyone ever seen Sirius B? It's on my bucket list. I've never seen it. Once in all your years, right? Van Manen star is in Pisces, but that's a really faint, isolated star. And this star here is by far the easiest one to see. So it's easy to find and easy to see. So get out there and observe a white dwarf for yourselves.
By the way, there's a very famous person who was born on a planet that goes around that yellow star.
That's
you know
right,
who
I
it is?
forgot that.
You? No, well, I was born, but this is before. This is a famous person. I don't know where I was. I think I was hatched. I wasn't really born. I was hatched. Spock.
Mr. Spock, yep.
And because that's an exoplanet, so I think our speaker, you're going to give us about a half hour on the planet Vulcan and everything about it. So I'm putting the pressure on.
Oh, yeah,
let's go
the
from there.
planet Vulcan is around, yes, there you go. So next slide, oh, it's 16 light years away. So here's the object for the month, M2. I would throw the distance up there for fun. This is another easy object to find, right? I always go to Beta Aquarius, and it's about a third of the way from Beta Aquarius to Enif up there.
It's actually a right triangle too with alpha, either way,
Yeah.
but it's easy to find.
Yeah. All right, so go ahead and talk about it.
What do you want to say? I don't know.
I don't know, it's a globular cluster.
Anyway, it is the naked eye if you live in the dark area. It's about 6 magnitude, a little fainter than 6 magnitudes. You can see it with the naked eye. I picked it up with binoculars from an area where my skies are magnitude 5. But it's a beautiful sight. We'll go now. I was talking before, we've kind of taken over the Observer's Challenge report from Roger Iverson. We're not going to be as elaborate, but we're putting it on our website. And I think Maria is already thankful. Thank you, Maria. Where are you, Maria? I know you're out there somewhere.
She's way in the back.
There you are, hiding in the back. Okay, I won't have you come up front and take a bow. But anyway, we're going to put it on the website. And so I'm going to show you now this is a wrap-up of what we got for that. This is last month's Observer's Challenge. And we'll go to the first slide. How did that happen?
I don't know.
You didn't
I put up what you sent me.
Well, we'll go to the next slide then.
No, it won't be there.
Okay, back
Go back,
up.
go
Well, I
back.
tell you what, just go to our website and look for it. I don't know, apparently what I sent out didn't go through. That's,
Whatever system Glenn is using, I'll keep this story short. his
Please.
computer or something takes a beautiful PowerPoint presentation, grinds it up into little bits and sends it to me. And then my job is to put it all back together again.
I'm looking at Al, our newsletter guy, going, yeah, I know what you're talking about.
It took 4 or 5
It went into the black
slides.
hole and got
Yeah.
It took about 4 or 5 slides this month for Glenn's slides to reach me. So I only put up what I could piece back together.
I'll just drive to your house and here's the whole thing.
But look, I don't know, I'm sure everybody's taken a look at M2, but it's one of the showpiece globular clusters in the sky. And if you've never seen it, then you owe it to yourself to get out there and look at it. An 8-inch telescope, so a moderate aperture with proper magnification, will start to show some resolution of the cluster stars. If you really, really want to see it in all of its glory, come to the clubhouse on the weekends that the place is open and look at it through the 25-inch telescope. It'll blow you away. It is a spectacular globular cluster, and you really should check them out. It's right up there with M5, M3, M13. There are quite a few of them that I consider to be the showcase globulars, but this is one of them, and it's just spectacular.
And by the way, one of the challenges for that was there's supposed to be a dark lane on one edge of this cluster, and it's basically visible right about in here. It doesn't show all that well, but it's right into the top section. And in my telescope, the 10-inch, I didn't see the dark lane, but the nucleus was kind of flattened. I think that's the edge of the dark lane. So it's a kind of a nice sight. And again, I resolved it kind of scattered with a 6-inch telescope, so you don't need a huge aperture to split this one up. So it's a nice sight.
Whose picture is that? Is that Mario?
No, you know what, Mario, we were arguing about that, or talking about that last time. That's something I got off the internet.
Oh, all right.
Mario's picture would look like that. It's a beauty. I'm looking at some of the red giant stars that are in that cluster, and Mario had a picture very much like that.
Mario's picture would have diffraction spikes on bright stars, and
That one does
too.
That one does too.
Yeah.
I can't see them from here.
I compared this one to the Mario's, the back and forth, there was a slight difference, so it wasn't, but Mario's looks a lot like this. Anyway,
In processing, you can make a big difference in terms of how dense the cluster looks. So you can take the same original data and come up with 2 very different images.
But if you go to our website, the observers section, then you'll find the observing report. And they're basically 4 pictures, and then there's my sketch as well of that. So we'll go on.
Glenn, just FYI, my diffraction spikes are rotated 45 degrees from that.
Okay. But Mario's was very much like this. Again, it'll be on our website, Mario. I apologize that I screwed up sending this stuff to Rich. It stole, I think somebody stole it.
It's not your first screw up, it's okay.
We're going to start a conspiracy theory. Somebody's stealing my, I didn't hear it.
All right, next slide, next slide,
It's
next
the
slide,
flat earthers.
next slide, next slide.
Okay, this is the current one. And it's the Deer Lake Galaxy Group. It's near the galaxy NGC 7331 rather. I've tried for it already. No, like Rich and I were looking through the 25-inch telescope at the club. And I remember seeing 2 fuzzy patches, which could be galaxies, but they were on opposite sides of the galaxy. And these were all on the eastern side. So there was, the scene was terrible that night.
Well, that was the problem. I was up there again with Steve and Phil, and I could see these 3 galaxies here, this one, and this one, and this one. They just looked like just
small.
ghostly, if you can imagine such a thing. They're barely there with the averted vision and just letting your eyes sort of soak in the image. I could actually see 3 of them, but that was all. In the 25-inch, that was a tough sort of thing. Stefan's quintet was there also, but pretty faint. You need a really dark sky to see Stefan's quintet.
Yeah, this is Doug Paul's picture, I believe, and there's Stefan's quintet right down there. And again, the Deer Lake is up near the top. And, but anyway, there's a consolation prize here because NGC, the 7331 is visible with a small aperture telescope. In fact, some people call it one of Messier's misses because if he'd been in that area, he would have probably picked this galaxy up as well. The others, though, they're all about an arc-minute across in diameter. We're talking very small, and we're talking 13th, 14th magnitude galaxies. So, but anyway, if you don't want to try for those, try for NGC 7331. It's a beautiful sight. And that, again, you can pick up with a small telescope.
It's hard to see in this constellation chart, but I always struggle finding 7331. It always seems to be in such an empty spot. But
Yeah.
then, does that have a pointer on it? Can I just take it from me for a second? Here, you want one? Here.
Oh, we got one?
Well,
Holy.
all right, well, this is old school, look at that.
Oh, I like that.
Where did the batteries go? Where did the batteries go?
There's no batteries, right?
It works. So you start from ATMoB, and there, I don't think you can see it, but there's a little double star right there. And that's see, what do you think those are, like 7th magnitude? Yeah. So about 7th magnitude, that's how you find this thing.
Those are probably the stars right here.
Once you find that double star, which is pretty easy, then you can find the Deerlick group, or at least 7331. And I'm not sure Messier would have ever seen that, because I think it's a pretty faint galaxy. 47 million light years away. They get pretty faint when you start to put some distance between you and the galaxy. All right, you ready to go on?
And speaking of faint galaxies,
Here are your challenges.
the challenge is, first of all, can you even see any of the Deerlick galaxies? And if you can, try Stephan's quintet. And we have seen that with a 25-inch from the clubhouse, so that's a possibility. But
When I was up in Maine with Bruce, under some pretty dark skies, I could see Stephan's quintet pretty clearly in a 14.5-inch.
yeah.
So if you have dark skies, you can see those galaxies. They're kind of cool. Yes, sir.
We did see it in the 25 the last time we were at the clubhouse a week ago Saturday.
Yep.
Joe Henry saw it.
Oh, good.
So we had a nice atmospherium on the phone. We pinpointed the area. The trick to seeing galaxies typically, I found over the years, is wait till they're on the meridian, prime meridian, when they're at their highest point in the sky is when you'll see them. You'll have about a half an hour on either side. And it's surprising how much the atmosphere interferes with the visibility
Yep.
in our light polluted skies.
Sure.
So I've seen Stephan's quintet probably 10 times in my life, and it's harder every year, partly because I'm getting older, but also because the skies are more polluted. Anyway, during the prime meridian, they're at the highest point on good transparent night. That's the best shot to see them.
Perfect.
By the way, Phil Harrington, in his book, It's Cosmic Challenge, he mentioned those particular galaxies as a challenge for medium-sized instruments. We're talking 6 to 9.5 inches. He says it's a challenge for them. I'm sure you're out in the desert, and it's probably more 9.5 inches than 6 inches. You could see that. Okay, now let's see what we got here. That slide came through. All right, if you're a fan of Outer Limits, and you're over, oh, it's most of us, I guess. How many of you remember Outer Limits, that TV show? They had a bunch of galaxies. This was one of the galaxies in that picture. It's a beautiful edge-on galaxy. This is NGC 891. And I checked this out with my 10-inch telescope a few nights ago, couldn't see a thing. Now again, I live in magnitude 5 skies, and it was not way up there just yet, so I'm going to give it another try. It should be picked up with a 10-inch scope, but again, it's difficult.
This galaxy is faint. It's
10th magnitude, and it's about 12 arc minutes across. That's almost half a moon diameter across. And again, it's pretty much edge on. They say it's a lot like our own Milky Way galaxy, but that's the challenge for December. I put that out now just to give you a heads up. You know what's coming up in the future here.
pretty easy to find the spot. It's easy to get to the spot. That's not the challenge.
Yeah.
The challenge is actually seeing that galaxy. It's pretty faint.
So anyway, just to summarize, we've already looked at M2. We've already got the reports out there on the website. That was Messier 2. The one for this month currently going on again is the Deerlick Galaxy Cluster Group. Challenge yourself for that if you have a big scope. And then ahead of time, during the December month, it's Galaxy 891. I am going to give, that should be visible with a good 10-inch telescope, even from slightly light polluted skies.
And if you do take the time to look at any of these objects, please write up a short report and submit it for at least for future observers. All right, that was the beauty of Roger's Observers Challenge. He would publish that, it was on the web. He's gotten thousands and thousands of hits. And a negative observation is not a bad thing, because with this instrument and these sky conditions, I couldn't see it. That's important sometimes for people to know, so that they're not beating their head against the wall because why can't I see it? Well, I should be able to, but man, maybe not. So negative reports are not bad. So go out and try it. It's there. You can see it. It's just a challenge. That's all.
Okay, I think there's one more slide. Okay, Rich and I did a beginner's star party. What's that on the?
I can't remember.
Oh, there it is, the 26th, last Saturday, October 26th. And basically, we did a review of the autumn skies, and we're going to make this a year-long thing. We're going to go to the January skies, or the winter skies in January, then spring in April, and then summer sometime, probably July. And anybody it's a newbie to astronomy, or you have been away for a while and you want to get reviewed or renew yourself with the evening sky, it'd be a fun thing. About 20 people
Yeah,
showed
we had
up.
about 20 people for that. It was pretty good, it was good, fun.
So anyway,
Do that again.
That's our galaxy.
And that's our galaxy, right?
That's in the south.
and that was, when we were doing that, we wondered if it was going to tick off all the astro images that are on there. There's an observer's night, obviously, and all the people are out there taking images, and we get this green laser going back and forth. And you were out there, Al. Did we ruin any of your
Suns.
pictures?
No.
Okay,
Gary, what's up?
Are we still gonna have the small telescope night?
I would like to, I still would like to do that.
Yeah, the whole thing, I think, on top of all things, Richard's got the star parties going on, and there's just so much going on, and then you have the weather dependency and delays like that. I was talking to Rich about, I don't think we need to do these beginners things every year. So I'm looking at possibly next year we'll go back and do the small telescope things. A bunch of projects we had that we'd like to do. And maybe this one, the beginners thing, we do every couple of years. So stay tuned on that one, because that's going to be a fun thing too.
Yeah, like, keep it like, I don't know, I'll bring a 3-inch refractor.
Yeah?
We'll play with that. It's small telescopes. So you know that you can still do observations if you don't need a 25-inch telescope to do it.
Oh, yeah.
You can get out there and play with the small stuff too, so. All right, next slide.
I think that we're going to the,
Right, so here's the observing schedule for the clubhouse around the dark of the moon. So the end of November and towards the end of December. And I think that might be it for this report, but I think I've got my star party slide next, so if you can click to the next slide.
at this
These are all
point,
published in the newsletter anyway.
okay, I'm going to turn things over. Just keep
All
looking
right.
up.
Thanks, Glenn.
Clear skies.
So, nice job, Glenn.
All right, we are Sarah. The talk title is The Grand Diversity of Extrasolar Worlds. Sarah is an assistant professor of physics at the MIT Kavli Institute for Astrophysics and Space Research. She studies exoplanetary science with an aim to understand planet formation and evolution, orbital dynamics in interiors, atmospheres. This talk will focus on the remarkable diversity of extrasolar worlds and discuss theories for what drives this variety. She will specifically highlight intriguing properties of the orbital architectures of short-period planetary systems. Over to you.
Okay. Great. Can you hear me all right?
Yeah.
Great. Yeah, it's really great to be here with you today. It's also really cool to talk in this room. This is like one of the very first rooms that I gave a research talk in when I did like a summer project here as a college student. So it's kind of
down the lights.
a cool experience. But yeah, so I'm really excited to chat about exoplanets, which are planets around other stars. And I think one of the things that I'm really excited about exoplanets is just the incredible diversity that they show. And it's really fun to think about all the things that make them that way. Why do planetary systems have such variety? So I'm going to talk a little bit about that today. Okay, so I think the question of whether there are other worlds out there was kind of really one of the biggest and oldest kind of fundamental questions of humanity. Surely our ancestors must have looked up at the sky and just wondered what was out there. I really like this quote from the Greek philosopher Epicurus, who was at least said to have, quote, that there's an infinite number of worlds, some like this world, others unlike it. But of course, for most of human history, the only planets that we knew about was those in our own solar system. Ancient humans only knew of 5 planets other than Earth: Mercury, Venus, Mars, and Jupiter and Saturn. And then it wasn't until telescopes became designed that they were able to discover Uranus in 1781 and Neptune in 1846. But at this time, they must have speculated, but wouldn't be able to know whether there were planets around other stars. Of course, they might have thought that there would be. And so it was with the design of telescopes in the last half century or so that astronomers kind of gained the ability to be able to even start to look for planets around other stars. And they started to discover them. So it was in 1995 that the first exoplanet around another star was found. This was a planet around a star called 51 Pegasi. And this planet that was discovered is a Jupiter-sized planet that goes around its star in only about 4 days. This discovery was so monumental that it gave these discoverers the Nobel Prize in 2019. And this planet is an example of a class of planets that we now know of as called hot Jupiters. And I'm going to talk a little bit about those more later on. So since that first planet discovery, we've discovered many, many more now. And I would like, I'm curious if you have a guess as to how many exoplanets have been discovered yet. So maybe, okay, raise your hand for between 1 to 10, 10 to 100, 100 to 1,000, 1,000 to 10,000, and 10,000 to 100,000. Yeah, so the answer is actually it's hard to exactly define, but this is generally in this range right now. It's hard to define exactly because we have planets that are called planet candidates that we think are planets but need follow-up observations. If you include planet candidates, it's like 17,000, but if you include just confirmed planets, it's around 6,000 or so. And so yeah, it was just last year that there was sort of this milestone that NASA was really excited about, that they confirmed 5,000 planets. And the numbers of discoveries have just accelerated. We discover more and more every day. But this is just talking about the planets that we have, actually observed around other stars. But this is just really the tip of the iceberg of what's out there across the whole galaxy. So I'm curious if you have a guess as to the number of exoplanets that might exist in the galaxy. And of course, this is an estimate, but so raise your hand if you think it's 10 million, 100 million, 1 billion, 10 billion, or 100 billion? Yeah, so most people go 100 billion, and that's kind of a good estimate. And the reason that we know this is because there's about 100 billion stars in the Milky Way, and we know that statistically speaking, there's about a planet per star, or probably even more actually, more stars than more planets than stars. But this places around about 100 billion stars in the galaxy. Sorry, 100 billion planets in our galaxy. Then if we kind of expand beyond and talk about other galaxies, like the Andromeda galaxy, then we can really start thinking about just how many planets must be out there. And if we look at the many, many galaxies that we see across the sky, like this image from JWST, where every dot of light here is a galaxy, then it really starts getting kind of mind-blowing, right? Because there's trillions of galaxies in the universe, and then if we say that each one of those has around 100 billion stars or so, and all of those have planets as well, then it just blows your mind, right? And to me, I find it kind of humbling that, in a way, to think that our little planet is just like this one tiny little ball of rock that's in this cosmic, spectrum of other planets. And it's just, I think sometimes when I'm worried about my own stuff in my life happening, I think about that and just think about this big picture that we're a part of. But so, now that we've been able to start to discover all these planets around other stars, we can start addressing some of these really big fundamental questions that we've all been kind of wondering about throughout human history. So questions like, how is it that planets even form? Like, why is the Earth here? Why why is Jupiter there? What's the formation process like? How common is our solar system? So our solar system has this like pattern of these kind of inner smaller planets and then the outer gaseous planets. It's all very flat. It's like the orbits are pretty circular. So how common are other planetary systems like that? Or is our solar system more of like an outlier? We can also start to ask kind of one of the big questions in our field is how common are habitable planets, which we define kind of loosely as those that might sustain liquid water on their surfaces and potentially sustain life like we know it on our Earth. And then, yeah, that kind of million-dollar question of how common is extraterrestrial life? So these are the questions that really kind of motivate and inspire exoplanet astronomers like me, and we try to, work towards these. These are big questions that we're still a long ways off from being answered. And in some sense, we're still just trying to get a picture of like what's even out there and understand some basic properties. And so this is kind of our big picture goal, but we have to kind of work our way towards that. So let's talk a little bit about what we even know about the planets that have been discovered thus far. All of the data of like just kind of fundamental properties of exoplanets is all publicly available at the NASA Exoplanet Archive. It's kind of like a just big database of known planets, and as of a count a little bit earlier this year, they report over 5,000 confirmed planets, as well as over 7,000 planet candidates, which are coming from the TESS mission, which is an exoplanet hunting satellite that is managed at MIT. So let's take a look at some kind of data from these exoplanet populations. So here I'm plotting the planetary radius and the planetary mass plotted as a function of the orbital period or the time that it takes to go around the star, and that's correlated with the distance from the star. So planets over here are closer to the stars than ones over here. I'm showing you both radius and mass depictions because they are obtained from different methods, different like detection methods, and they tell us a little bit different information. So one thing to note here, there's a lot of interesting things just to see in these plots, but one thing to note is that many of the exoplanets that we know of are much closer to their stars than Mercury is to our own sun. So Mercury's orbital period is around 88 days, and we've discovered many planets that orbit much closer to their stars. Another thing that we can see are that there's some kind of distinct groupings here. So one grouping are these very massive planets, like Jupiter-sized, and they orbit very close to their stars, have orbital periods of just a few days. These are the hot Jupiters, and that the first exoplanet that was discovered is an example of one of these. You can also see that there's this really big collection of planets that are in between the sizes of Earth and Neptune. So they're in a size class that we don't have in our own solar system. And we kind of divide these up into actually two groups. So the super Earths, as we call them, are thought to be kind of scaled up rocky planets. So like they're like the Earth, but probably just a little bit kind of larger in size. And then the sub-Neptunes, these ones are either kind of like scaled down Neptune-like worlds, so they're just probably have rocky cores with thick hydrogen helium atmospheres, or they might be like fully water worlds with large-scale oceans. We're not quite sure what those are dominantly like, but those are the theories. We can also see that there's some planets smaller than Earth, and then some of these planets in between the sizes of Neptune and Saturn. And then also we can see some kind of more analogs of Jupiter in our own solar system that are on much more distant orbits and are pretty large planets. Also, I want to say too that these planets are so diverse, they fill almost the entire space. And the regions that they don't, like over here, there are probably planets here too. These are outside of our detection capabilities currently, because they're small and very distant planets. So there's probably planets here too. And we're just working towards being able to detect those.
You can't see an Earth, for example.
Exactly, yeah. But there's many people that are trying to work on getting better methods to be able to detect true Earth analogs. Another thing that I want to note about these pictures is that, like the relative occurrence of the different, so maybe if I go back to just look at this kind of collection of points here, the relative occurrence of these doesn't necessarily mirror their true occurrence rates, because there's different detection biases for different types of planets. So for instance, it's much easier to detect really big, close-in planets than it is smaller planets on more distant orbits. But astronomers can very carefully account for all of those detection biases, account for the statistics, and measure the true occurrence rates of these different planet populations. And one thing that I want to highlight with that is that these guys, the super-Earths and sub-Neptunes, these are crazy common across the exoplanet population. About half of sun-like stars have those. And that's kind of weird because we don't have one in our own solar system. So it's not like to say that our solar system is in the other half of the group isn't that weird, but it is quite interesting that these are so ubiquitous, and we're trying to understand more about what those are like, because they seem to represent kind of the dominant mode of planet formation in our galaxy from what we can tell so far. I want to talk just a little bit about how all these planets have been discovered. Many of you are probably already aware, but just in case, it'd be good to review. So the main kind of workhorse method is the transit method, where we observe planets that cross in front of their stars from our perspective on Earth. And when they do so, they cause a dip in the observed starlight. The amount that the starlight dips is dependent on this planet's size. So it's like this dip is equal to like the ratio of the areas of the two. And so this method is useful because it can tell us about the planet's radii. And also when we observe the dip happening repeatedly, that gives us the planet's orbital period. Also, this can be done using ground-based telescopes, like some of the big scopes, like those are the Keck telescopes in Hawaii. You can also do these with many smaller scopes, and probably people here have observed transits before. You can also do this with space-based telescopes. There's pros and cons with space-based telescopes like TESS. You don't have to worry about the atmosphere. You can observe at any time. Like with ground-based telescopes, we can get many telescopes observing at once, and that can sometimes be beneficial as well. So there's pros and cons. The other main method for detecting exoplanets is the radial velocity method, and this relies on the fact that the star is not actually perfectly stationary when the planet's orbiting around it. The planet's gravity is tugging on the star as well, and it's not quite as dramatic as this picture shows, but the star is wobbling, and they're orbiting around sort of a common center of mass. And so what we are actually detecting is the motion of the star towards and away from us. And the analogy for how this is detected, just to say, what we're detecting is the radial motion, so radial here meaning towards and away from us, and then the velocity meaning like how fast the star is moving towards and away from us. But yeah, the analogy for why this works is if you're outside and you hear an ambulance pass you by, you might notice that when it's approaching you, the siren sounds higher pitched. And that's because the sound waves are compressed, giving it a higher frequency, and so it sounds higher pitched. And then when it is receding away from you, the sound waves get stretched and it sounds lower frequency. That's the Doppler effect. And light does a very similar thing. So light, when it's approaching us, the light waves get compressed and become a little bit higher frequency or bluer. And then light, when it's receding from us, is a little bit longer frequency or redder. So this is the Doppler effect applied to light. And this is not it's not a very extreme shift. It's just a tiny little shift of the spectrum of the star. But very, very sensitive instruments can pick that up and can detect that there's a planet orbiting around that star. The amount that the star wobbles depends on the planet's mass. So this is not only an ability to just find the planet, but you can also tell from that measurement how big that planet is in terms of its mass. So it's really useful when we can actually use the transit and radial velocity methods in tandem. So if you have a planet for which you can observe both of these, then you get the planet's radius and its mass. And when you get radius and mass together, you get constraints on the density of the planet. And that's really useful because it can allow you to learn more about what the planet must be made of, like what's its composition, rock or fully gaseous planet, something in between. And so these methods are not just used to detect planets, but also to characterize them and to be able to learn more about what they're actually like. So these two methods have been the main workhorse for discovery of planets. There's a whole bunch of other methods too, which are kind of shown here, but the main, like, transit and radial velocity are these two bottom colors here, and they've accounted for most of this rise of detection over the last 30 years or so of discovery. And so now that we have such a large planet population, we're really in the realm where we're moving, this has been a while that this has been the case, but moving away from just detecting more and more and being able to start to characterize them and to then answer questions about what's making them this way, to try to answer theories for what creates the planets that we see. And so that's what I do in my work. So I'm predominantly a theorist, as they say. Like astronomers are kind of divided into theorists and observers, so I'm more on the theory side. But what that means is I try to answer questions about the planet population, meaning I look at observations of unusual kind of types of exoplanetary systems, maybe like case study systems, or populations of planets where a set of planets display some interesting behaviors. And I try to use physics to explain what creates that. And specifically, I look at what we call the orbital architectures, which is kind of, I'm going to describe more in the next slide, but I look at sort of patterns across the orbits of planets within a given system and try to piece together how those planets must have formed and evolved to give rise to the collection of orbits that we see. So this phrase orbital architectures can sometimes be confusing, so I kind of like to just draw an analogy for the normal usage of the word architecture is when we think about buildings and we think about things like basic aspects like the dimension or the number and layouts of the rooms, but also like what the building is made of and the style and type of the windows and doors and so on. And so when we think about exoplanet architectures, you can kind of draw analogies here, like we can think about the distances that these planets are from the star, or the number and types of planets within a given system, what those planets are made of, how they correlate between different planets within a system, the shapes of the orbits and the orientations of the orbits, and similar questions like that. Okay, so I wanted to talk a little bit more about these planetary architectures and give some examples of the interesting things that we've observed about them. And so I'm going to kind of highlight a few different aspects of architectures. First is I want to talk a little bit about the separations between planets. So some planetary systems are more spaced apart, whereas others that we found are very, very tightly spaced together. So one example, probably the most famous example of a very tightly spaced system is this one called TRAPPIST-1. So this planetary system, you might have heard of, it's extraordinary. It has 7 roughly Earth-sized planets, a few of which orbit in the habitable zone of the system, but they orbit a teeny tiny star that's less than 1/10 of the mass of our sun. And if they orbit in such a small region that if it was like put in our own solar system, it would fit in this tiny little region here. So it's like, it's a system of terrestrial planets, but on just a massively scaled down size, such that those planets are actually quite close to each other, and their perturbations between the planets are actually pretty extreme. Another thing that we've studied are the relationships between the sizes of planets within systems. So, for example, this is just like a kind of random collection of planetary systems that have been discovered where here on the x-axis is the star-planet separation. So like these are further out planets. And then the sizes of the dots correlate with the observed sizes of the planets. So we've actually discovered a lot of systems in which the sizes of the planets are pretty uniform within a given system. And I'm going to talk more about those towards the end. But we've also discovered ones where the sizes are a little bit more diverse, like this one. And then there also is a tendency for a collection of systems where the sizes appear to be somewhat ordered, like the one shown here. So we can, by studying these size relationships, this gives us a little bit more information about their formation as well. Another aspect of these architectures are what we call the eccentricities, or how elongated the orbits are. So all the planets in our solar system are pretty circular, but that's not the case for all exoplanetary systems. And in fact, earlier this year, I was involved in the discovery of the most eccentric planet that we know yet, which has this long name here. But if you were to put it in our solar system, it would look like this on this very eccentric orbit. Like this means that it gets very, like, its distance from its star changes quite a bit over a single orbital period. It gets very, very close to its star and then very far away. So it kind of gets flash heated at those times. And as part of this discovery, we had to try to explain what it was that gave rise to this very eccentric orbit. We don't think that planets formed like this, but rather there had to be perturbations between, at least in the case of this system, the planet and another star in the system. That perturbations between them gave rise to this very elongated, unusual orbit. Yeah?
What's the orbital period of that planet?
This one is 165 days, I think. Yeah, and its eccentricity is 0.94.
Wow.
Yeah. Yeah, so another, kind of on a similar note, another thing about, another feature of architectures are the inclinations between the orbits. So as I mentioned already, our solar system planets are very coplanar. It's just a pretty small few degree dispersion between the orbits. But like, I guess maybe it's not a surprise at this point, but that exoplanets show a diversity there. That some planetary systems can be highly misaligned, where the orbits between planets can be like 90 degrees or more. And again, we don't think that they formed this way, but when you see a planetary system like this, it indicates that it underwent some kind of chaotic, dynamic history that created the system to look like this, and then we have to try to put the pieces together to understand how that happened. On a similar note, another thing that we look at is not just the alignments between the orbits in a given system, but also the alignment with the star. So, and that's called the stellar obliquity. So the stars spin on their axes. So like our sun has a rotation period of 20-something days. And so this vertical line here is representing the stellar spin axis. And then this line here is the orbital axis of the planet, which is perpendicular to the orbit plane of the planet. And in our solar system, those are aligned, like that's what we would expect, that the systems all form in kind of this one kind of plane, and that they all would spin in the same direction. But we observe many exoplanetary systems where the star is very tilted, and we have to try to understand how it could have gotten that way. Again, we don't think it formed that like that, but that something happened to create it that way. So yeah, these are just a few examples of the properties of planetary systems that are observable and that we can try to kind of piece together to learn more about what happened to them, what dynamic history created the things that we see today. Yeah.
Yeah, let's see, you see, you didn't put up orbital resonances.
Right.
I think it's actually super important.
Yeah. Sorry, it's checking time here, but yeah, definitely. So resonances, for those that might not know, there's planets where the orbital periods of adjacent planets are related to one another by a ratio of simple integers. So, for instance, you could have one planet on a 10-day orbital period, another on a 20-day orbital period. The ratio of their orbital periods is 2 to 1. And these, like Jupiter's Galilean satellites, are in a resonant system. Their orbits are like 4 to 2 to 1. And yeah, that's another thing that we studied and that we try to understand how they got into those configurations.
Pluto and Neptune is 3 to 2.
Exactly, yeah. Yeah, so resonances are really common in the solar system. They're actually not that common in exoplanets, surprisingly, but they are there, and we do try to understand them. Yeah, so in kind of the time that I have left, I wanted to kind of narrow in on a particular class of planets and discuss their architectures in a little bit more detail. And the class of planets I want to talk more about are these guys. These are these planets that are known to be super prevalent. They represent the dominant type of planet that's been discovered, and not only that, we think that they represent the dominant type of planet that exist out there. And so these guys, the ones that aren't represented in our own solar system, they're in this kind of size regime that we don't have. But these are the super Earths and sub-Neptunes. One thing that's really interesting about these planets is that they often come as part of a multi-planet system with very tightly spaced orbits. So an example of the first one of these that was discovered is the Kepler-11 system, which was discovered by the Kepler satellite, which flew like a decade ago or so. And these planets there's like 6 planets all within the orbital radius of Venus. And a really interesting aspect about these multi-planet systems is that they're very like well structured. So when I was talking earlier about planets that can be very eccentric or very inclined, these ones don't really show that. They're all very circular orbits, very coplanar. They're kind of just very nice planetary systems. Like if you were to ask like a kid to draw a planetary system, they kind of look like that. So they're very regular. And one thing that I find like still one of the coolest things that I was part of discovering was the fact that this regularity in the structure is mirrored in the physical properties of these planets. So that is that there is not only this regularity in the orbits, but that the masses and radii of the planets are also very regular within a given system. So I'm going to try to explain that a little more. So on this plot on the right-hand side, I know it's really hard to see, but like each row is a different planetary system, and like this x-axis is their depth separation from the star. The sizes of the dots represent the sizes of the planets. And if you kind of scan your eyes down through these various systems, you can maybe start to notice a trend that the sizes of planets within a given system look a lot more similar to their neighbors than you would otherwise expect. So like for instance, these guys are all very small, these ones are more medium, and like it kind of extends across. It's not perfect, they're not exactly the same size, but there is this tendency that's very strong statistically when we run through. It's like a very, very strong effect in the data. This also is true about the masses of the planets. And in this plot here, I'm showing the planet mass and radius for a collection of planets in different systems where planets within a given system are connected by lines. So for instance, this is a 2-planet system, this is another 2-planet system, this is a 3-planet system, and so on. And you can kind of see here that planets are kind of, or systems are kind of clustering here. Like, these ones are very close to each other, these ones, and it kind of continues throughout. It's easier to convince yourself of that if I like show you what it would look like if there was no size collection. So this is like what you would expect to see if they were not at all correlated in their masses and radii between a given system. So you can see that they're much more clustered, they're much more close together than you would otherwise expect. This collection of observations, we now kind of know this as what we call the peas in a pod patterns, because there's a resemblance between these planets in a given system and a collection of peas in a pea pod, and that's literally what like our field knows this effect as now. I remember when I was working on this in grad school and like helped discover this, my advisor was like, you should go read some biological literature about how pea pods grow to like try to understand what's giving rise to this. So it seems like planets in these systems like to create identical copies of one another. And there's been many theories now for trying to understand why that's the case. There are some, ideas, but we still don't know for sure what's giving rise to it, but it's certainly telling us something about the planet formation process. And one thing that I just want to kind of close on now is talking about what happens at the end of the pod, so to speak. So the planets that we observe, let's say we observe 4 planets in a given system, but what dictates the edges of those pods, right? Like there's the inner edge and the outer edge, and maybe there are more planets that are in the system, like further out planets that we haven't yet detected. The observed ones might just be a subset of the full system. So one thing that I got interested in a few years ago was this question of, can we say anything about whether or not there are further planets out there? That is, can the outer edges of the observed planetary system tell you anything about the outer edges of the underlying planetary system? So I'm going to try to explain this a little bit in these slides, but what I explored was this idea of like, okay, we have all, this is not the full collection of planetary systems by any means, but it's a lot of those that have very high multiplicity. So 4 or more planets within a given system. And this is still not the full collection of that, but it was a sample that we looked at. And so these were all discovered by the Kepler satellite. The Kepler satellite could have discovered planets out to around 500 days in orbital period based on the length of time that it was observing the star field. It's a little bit, not a hard boundary, it's more fuzzy than that. But the basic idea is that there's a lot of space between the outer edges of the observed systems and the furthest period that it could have detected. So like if there were planets in any of this orbital period regime, there is a possibility that the Kepler satellite could have detected them. So why don't we see those? So what we did in this study was say, okay, what if there were, what if these peas in a pod continued? What if there was another planet just on the outer edge of each one of these? Hypothetically speaking, I'm not saying this is actually true, but like, what if there was another planet in each one with a size kind of resembling the others in the system and with a separation like what you would expect based on the other planets in the system? And then we said, okay, would those have been detected? Would those planets have been detectable by the Kepler satellite? So these yellow dots represent the minimum detectable sizes of those planets. That is like how big of a planet would have had to be there if it would have been detected. And what we see here on the right is the ratio of the size of the hypothetical planet relative to the minimum size of a detectable planet. And interestingly, this ratio is greater than 1 in all of these cases, meaning that the hypothetical planet should have been detected in all of those cases because it was bigger than the minimum detectable one. So this is, this is just a sketch of like kind of the statistical argument that we constructed, but what we were able to show in this study is that indeed we should have been able to detect more planets further out, but we didn't, meaning that there's sort of something that happens out in this outer parts that we observe, 4 or 5 planets, sometimes 6, and that there's something that changes, like they don't just go on forever, that there might be like a truncation, or maybe the planets just get suddenly very much smaller at further sizes. We don't really know exactly, but we were able to detect that these pods are like finite, which makes sense, but that the fact that we were able to see exactly where they end was an interesting finding that we kind of call now the edge of the multis. This might be somewhat analogous to what we see in our own solar system, where our inner terrestrial planets are kind of clustered in this region, and then there's this big gap until you get to the orbit of Jupiter with the asteroid belt in between. I'm not saying that this is similar to what we're finding, but it might be, like, we don't know that for sure, but the fact that we see this kind of, small rocky planets within a distinct transition to a different part of our own solar system might be analogous to what we're seeing in exoplanets. And so this is an example, I think, of where what we know about the solar system can help us understand what we're seeing about exoplanets. And also it kind of feeds back what we learn about exoplanets can help us understand the solar system better. So with that, I'll just summarize now by saying that the field of exoplanetary science, I think, is in like this very data-rich era. More and more planets get discovered every day. Like they're coming down faster than we can really process them. But all of this data, we're able to start to not just detect planets, but characterize them, understand their masses and their radii, their orbital properties, and try to piece together a good picture of what they're like, and understand why. So in my work, I specifically look at the orbits of planets and try to understand what drives such diversity, like things like the peas in a pod systems, or more bizarre systems that I didn't really talk about today, but try to understand the physics that drives all of this. And just highlighting that it's kind of cool that there's this tendency for planetary systems, at least these very tightly spaced ones, to be like peas in a pod. We're still trying to understand why that's the case, but I think it's kind of something that's very orderly that I wouldn't necessarily expect the universe to show such order, and I think it's really interesting. So with that, I'll thank you for your attention and take any questions.
So if I get it right, from what you said, that a lot of systems, maybe a higher percentage of systems are more condensed than our own, as far as their overall.
Yeah, I mean, the strong caveat there is the ones that we are observing. So there may be much more spaced out systems, but they're just harder to detect because it's so much easier to detect these very short period things. But yeah, among the planetary systems that we know, they're very much more tightly spaced, and they orbit much closer to their stars than our solar system does.
All this is within our Milky Way. All the studies within our Milky Way itself, right? Not in other galaxies.
Yeah, it's all in the Milky Way, yeah. Mm-hmm. Yeah.
But the planets that we're discovering basically have to have an edge on orbit so we can get the radial velocity or whatever. So that would leave out, I take it, any planets that are doing this. So do they know the percentage of stars or planetary systems that are doing this? What percent, we can also figure it out for a single star itself, just by the, is there a percentage of the stars that have that rotation in the plane of us?
Yeah.
What percentage of those have been discovered that have planets? You kind of transverse that to stars that are...
Yeah. So, yeah, you're totally right. There's a probability of transit, and it depends on the orbital period of the planet. So you're more actually likely to transit if you're on a short period orbit. So like a hot Jupiter has a transit probability of, I think, around 10%, but once you get out to like Earth-like orbits, it's less than 1% probability that the planet would transit.
Yeah.
But they're able to, like when they construct occurrence rates, all of that stuff, like it's mathematically accountable for. So like they can say, okay, we detected, 563 of these, but based on the fact that only 10% of those would have transit, we think that there's X amount more. So they can like essentially correct for that effect. And based on that, put together like true occurrence rates. So actually those hot Jupiters, even though they're very easy to detect, those guys are actually really rare. So yeah, you asked about like occurrence rates. The hot Jupiters, those are about 1% of stars have a hot Jupiter, whereas that's very different than these guys, which are about 50% of sun-like stars. We're not too sure about the occurrence rates of these yet because they're still kind of hard to detect. And these ones, I think, are about like 10% or so. Yeah, but that's all after you do that correction. Yeah.
Can you say something about microlensing?
Yeah, so I'm definitely not a microlensing expert, but it's a different method of detecting planets, where what you do is if you have a star with a planet around it, and that there's a background star that its light is kind of passing essentially through the planetary system that you're trying to detect, the light gets gravitationally lensed and thus like brightened by the mass around not only the star in the middle but also the planet. And microlensing is cool because like you kind of get it for free just by looking at this brightening. But it's harder to characterize planets with microlensing because it's kind of like a one-off event. You just see it once based on the motion, and then you can't go back and observe it. And so you can only get like rough aspects of the planets. You can just get like a projected separation rather than like true star-planet separation. And you can also only get a mass ratio of the planet to star rather than like a true mass. So it's like pros and cons.
Now that you got that slide back up there, why aren't there more cold Jupiters over in the radius category there?
Yeah, so that's partially because, okay, so there's multiple reasons. One is that all of these guys are transiting planets because we have their radii. So in order to measure the radius of a planet, it needs to transit. And Kepler was the workhorse for getting like many transit discoveries, but it only observed the star field for 4 years, so we're limited to like a certain period range for where it could have detected. And also the transit probability of those guys are really low. And so these ones were discovered by radial velocity, and it's much easier to detect those things because they don't have to be like transiting orbits, and some of the radial velocity stars have been monitored for like decades, so you can see really long period orbits and get further out there. Yeah, so it's like purely a detection bias. Yeah.
Concerning single versus double or multiple star systems, is there any correlation, number of exoplanets and so forth?
Yeah.
The stability of the orbits in multiple star systems?
Yeah, so when we talk about multiple star systems, there's like multiple genres, or I guess classes of those. So there's circumbinary planets, which are ones where you have a binary star and then a planet orbiting that, kind of like Tatooine in Star Wars. And those, we only know of around 20 of those, but that's purely just because they're really, really hard to find. They're probably more prevalent, and they're just, the detection is just really tricky. But so that's one class where you have the binary star and then the planet going around it. But then you can also have like a star and a planet and then a star on a much more distant orbit. Those are much more common, like we know of many of those types. And, but we do also know that that binary star can't be too close, otherwise the planets their orbits get gravitationally disturbed and then they like just, they can't form there. So there have been a lot of studies that show like, based on how close the binary star system is, it's like, if it's at like 1,000 AU, you're like totally fine, no issues for the planet. But once you get to like 100 AU or closer, then that planet like can't really stably orbit, and so there's like the occurrence of planets goes down as the binary gets closer.
What's the status on exomoons?
Yeah.
Are there confirmed candidates, or are there candidates that have not been confirmed, or any?
Yeah, exomoons, it's such an exciting concept, but it's been like this very frustrating search because there still aren't any confirmed ones. There are some candidates that were put forward, but they don't raise to the level where the community has accepted them as like true discoveries. But everyone's very hopeful that J2ST will actually discover these. I know like a few friends of mine have like proposals to observe with J2ST to look for exomoons. And I think that it's just a matter of time. And it's only just because we didn't have the photometric like capability to see those tiny signals until J2ST. So I'm hopeful, but yeah. Okay.
Any more questions? Thank you.
Oh, yeah.
Yeah.
So I think we have reached the close of the meeting. Next meeting is December 12th, 8 p.m. Just want to mention that we have a board meeting coming up on November 21st, 8 p.m. Because everybody is invited, right? Only board members can speak, others can attend. Okay. Thank you.
You should tell people that you will be sending the message out.
Yeah, we'll send the announcement as well. So.